Okay, let's go from here. We're looking for, well, not we're looking, but we've completed a handful of these things already. And then we were doing a problem here, the roller coaster problem. So we'll continue to work on that in a minute. And the new material that we're going to go over today from this section is integrating. And the integrating is like differentiating. You just do it component by component. And so we'll just do one quick example of that. And then we'll move on to the next section, 13.3. All right. So our problem from last time was this. This was the last page, so let me just take a quick picture of this. So this is from our notes from last time. We got the roller coaster thing. We found out that it hits the ceiling at t is equal to 1, and then it would hit the wall. If it went through the ceiling, continued through the wall, it would hit through the wall y equals negative 12 at some other time past 1 second or 1 minute or whatever. So we know that it hits the ceiling at t is equal to 1. We found the line equation for that. And so the only thing left to do is to get the rest of this information, or to get the rest of this question, which wall would you hit and where. So the where part is the last part that we need to do. And we know that when t is equal to 1, whether that be seconds or whatever time you're measuring with, we can just put 1 into the line, and that's going to tell us where it's going to be. We know it's going to hit the ceiling at 12, so we better have z is equal to 12 for that. But the x and the y is what we're gonna, the other part that we're gonna find. So let's see, L of 12 is what we're interested in, and that's putting, L of 1 is what we're interested in when t is equal to 1 into the L function. So we can just say this is negative 5, 0, 0. Plus 1 times t, or t is 1, times t, or plus t times 0, negative 7, 12. So this would be negative 5, comma, 0 minus 7, so that's negative 7. So negative 5, negative 7, and then here's that positive 12 that we're expecting, positive 12. So this is our point of intersection. Yes?
So when we say that it hits the ceiling at that point, so is it like the point after the ceiling that it hits like the second wall, like y equals to negative 12? So is it like moving from the ceiling to the...
Well, if it just continues in a straight line, it'll eventually hit the wall at whenever t is equal to 12 over 7. I don't know if I understood your question.
Yeah, I was just saying that if, like, say we chose, like, so we were rejected off the ceiling.
Yeah.
We're going in the direction of the ceiling, so when it hits the direction of the ceiling, does it like bounce off the ceiling?
No, it'll go through the ceiling. Yeah. I mean, yeah, that's what this would get us, is what happens if the ball went through the ceiling, or you. But if you didn't go through the ceiling and you'd bounce off, then that would be a different trajectory, and that would be a different line and a different point. Okay, so I got a visual of this. That's a little bit better than it was before. So this is the roller coaster. So that's the roller coaster. I got a slider in here somewhere. Oh, this is my slider. So this is the roller coaster, and this big point over here is where you're going to get ejected from. And as you get ejected, you're going to follow this line. And if you follow that line, when t, we're calling it n, I guess, when n is equal to 1 down here, we'll see that you've gone to the ceiling. Right? If you were to go through the ceiling, can somebody punch in on their calculators real quick? 12/7? About? Phones, whatever. 1 point what? 1.7. So if I go to 1.7, 1.4, 1.5, 1.6, 1.7, something like that, then I'm hitting that wall. That's the y equals -12 wall. And that's what I would hit. That's when I would have hit it if I were to go through the ceiling. Or if you didn't have a ceiling, and then you would eventually hit the wall. Okay? So that's the view, and here are the different viewpoints. You can twist this around and take a look. That red vector over here is your tangent vector. And this purple this is your purple roller coaster. The blue vector is pointing towards it's from the origin to the place in the roller coaster where you take off. Okay? All right, so let's see if we can capture all this. I think this is about as good a viewpoint as we can get. So this is your roller coaster. This is your path. R of t, this is your tangent vector, or this is your point over here, the point that you leave. So this is the position vector evaluated at pi. That's the time when we took off. And this vector over here, this vector is the derivative of the position, the roller coaster position value at pi, the derivative at pi, so r prime of pi. Yeah?
Did you give us pi?
Yes. You got ejected at t is equal to pi.
Oh.
And then you have the ceiling, this ceiling over here, z is equal to 12. And then you have the wall, the side wall over here, z is equal to -12. And then you have this line, y, yes. And then you have this line, L of t. And then this is the point where it would have hit the sidewall, but this is the point over here where it hits the ceiling. This is the point, -5. What was it? -5, -7, +12. Okay? Now I just wrote all over it and probably unreadable, but I can, if you want, I can make this this graphing calculator file available, but of course you would need to have graphing calculator available on your computer to view it. But all the computers at the STEM Center and the Back to Learning Center, they have the program graphing calculator. So if you want to look at it there, download it, view it from the different options, hide certain aspects, like if you want to hide, say I want to hide that roller coaster, I can, it's really simple to use, this program. All right. Okay, so there's a page of differentiation rules that could be important, that might be important for us. It shows that the derivative, the first two shows the derivative is a linear operator. If you've taken linear algebra, then you should know what that means. It preserves addition and scalar multiplication. The next one says that the product rule for a scalar function times a vector function also holds. And then the product rule for the dot product and the cross product also holds. And then the last one is the chain rule. The chain rule of these vector valued function for a scalar function also holds. Now, I'd be interested in doing one of these as a proof, one of those four. Which one should we do? Number 3, number 4. Number 3 and 6 involve a scalar function, and so in some cases that might be nice to see a scalar function involved so you can know what the hell the difference is between. So which one should we do? Number 3 looks okay. All right, let's do number 3. Let's prove this. And again, the approach for proving things like this would be to assume you have a generic function. You have a generic function, you have a generic vector function. And so what we could do is we're going to do this component-wise, so let's focus on the thing that has components, the u vector. And it's a vector function, so normally I call it f, g, and h, but there's another f in there, so maybe I'll call it x of t. And just the of t part just says that it is a function of t. The name of it is just x. So this could be like cosine t or something. And then y of t, that could be, for example, sine of t. And then z of t, that could be, for example, some exponential or whatever. Anyway, so that's about as generic as we can get. And we can proceed from here. We can assume that we have another function f of t that's all differentiable and nice and stuff. So let's take a look at what f of t times u of t is equal to. Now, f of t times u of t, I'm going to need a little bit more room here. Is this dot over here is actually a scalar multiplication, and that's where you're going to have to look at the dots and say, is that a scalar scalar? Is that a vector dot a vector? Or is that a scalar times a vector? And in this case, we have a scalar. The function, I'm calling the function a scalar because there's no vector to it. And so the u is a vector valued function. Is defined as x of t, y of t, z of t. So this is going to equal to a scalar. Remember, you distribute that scalar among all the different components. So I'll just write smaller here. F of t times x of t, f of t times y of t, and f of t times z of t. And now I want to take the derivative of that. So I want d dt of this thing. I guess I should put my arrow going down because I'm going to need more space. So let's take the derivative of each of them. Now each of them component-wise looks like it's a product, so I have to do the product rule for each of them. So let's see. This is going to be a derivative of the first times the second plus the first times the derivative of the second. So that's the first component, the product rule for the first component, and then I'll have the product rule for the other components as well. Derivative of the first times the second plus the first times derivative of the second And then the last one, the same business. And we're going to do the derivatives. So now let's split this up into a couple of vectors. Maybe for each of these vectors, I'll split them up here so it looks like I'll be adding two vectors. And so let's see, we have f prime of t times x of t. And then I'll take the second one, f prime of t times y of t. And then I'll take the third one, f prime of t times z of t. And so what I did was I split that up, and so I'm looking at the other terms. That's f of t, x prime of t, f of t, y prime. This is the times. And then f of t z prime of t. So the ones in the circle are on the right side, the ones that are underlined are on the left side. And so if I focus now and look at the ones that are the left vector here that I'm adding, I see that there's a scalar f prime of t that I can take out of this vector. So I'll say f prime of t out, and then I have x of t, y of t, z of t. And then I'll do the same thing over here. I have f of t, a scalar that I can take out. They're all the same, so f of t I could take out. And then what I have left in the vector is x prime, y prime, and z prime. And then I just note that this is u of t, and the second one is u prime of t. And so that's it. So f of t, or f prime of t, times u vector, as defined up there as my u vector, plus f of t and the u prime vector. If you were to take the derivative of u, then you would just piecewise differentiate that. And then that is the exact right-hand side of that property that we're looking for. Okay? And if you've proven a lot of things, people usually say QED. You guys know what that stands for? Something Latin. In English, it translated that which has been proven, or that which has been proposed, or something like that, yeah. I don't know how to speak Latin. So, quod eras demonstratum. What? Hopefully it's right. All right, so that's the end of the proof, and we've proven this one right here. Okay. So beyond derivatives, let's take a look at integrals. And integrals have the same properties, and they're just as I don't want to say simple, easy. they're the same thing. You do piecewise, and so all the stuff that holds for derivatives kind of holds for integration as well. And we would have the same similar properties, except I don't think I've listed them. So we'll just go with a definite integral. So taking a definite integral of a vector function would be the same thing as doing the little pieces of those vectors. So whether you're doing the definite integral or the indefinite integral, you're going to do things piecewise for vector value function. The only subtlety with the indefinite integral for vector valued function is that when you do an indefinite integral, you get a plus c for each of those. Remember back in Calc 2 where you used to get a point off for forgetting to put a plus c there? So there's a plus c that goes for the different components. And sometimes what people tend to do was they take all the plus c's and they put it all into one vector, so that the c vector is actually technically equal to c1, comma c2, comma c3. Yes? Oh, this must be c3.
Another thing I found out was that, if you're doing the equation below, so you're going to find c, you can just, in this case, take the integral from 0 to whatever, or take the interval from 0 to t of each of those, and then add all of your.
Sometimes that works. When you put 0 in, you don't get 0.
No, the idea is that I have to show you the visual.
Well, we'll take a look at it later. All right, let's do an example similar to a homework problem that you guys might have. Here we have r prime of t given to us, and they want us to find r of t, the original function. So we're essentially backtracking, taking the antiderivative. And then they give us a little r of 0 information that we may have or haven't known. So let's take a look at this. Let's take the antiderivative of r prime of t dt. The fundamental theorem of calculus says that this should be the integral of each of these components. So let's take the integral of each of these components. Now this is written in IJK form, but we can switch back and forth. So we can choose to have, I don't know how you guys want to do it, we can choose to have the arbitrary constants for each of the components, or we can just have one vector component outside of that. Let's keep it outside. Okay, so let's take the antiderivative of each of these things, and then in the end, we'll remember that there is a constant vector outside instead of constants within the components. So the antiderivative of t to the 5th, I think it's t to the 6 over 6. Is that right?
Yeah.
So t to the 6 over 6 in the I direction. The integral of e to the t is e to the t in the j direction. Yeah.
I did this problem, so I'm familiar with the method.
Okay.
You have to use the integration that hurts.
Yeah, I know. But I just want the answer. All right, fine. I'll help you guys out. We're going to integrate, what are we integrating? 4t times e to the 4t with respect to t. Yeah, could have came up with that. So I do expect you to be able to do this, right? Except I don't want to spend too much time on integrating in class. You guys are integral experts already. So if you would have done the integration by parts, you would probably say t e to the 4t minus 1/4 e to the 4t. Okay? And then you have that extra constant vector sitting outside. So the constant vector are the components of the constant vectors are the arbitrary constants that came out of each of these things. So this would be your potential R vector. So we're given R prime, so this is potentially your R vector. But maybe I should say your R vector but we have to have this extra condition that R of 0 has to equal to ijk. So we'll write that down. R of 0, what? So we should put R of 0 into our potential vector over here. So 0 in for t, which is going to give us 0. I don't have to put 0 since I'm using ijk, but I think it would be good to actually put it down here. And here you have 1 in the j direction, because e to the 0 is 1. And 0, and then e to the 0, and then you have a negative 1/4. So you have a negative 1/4 in the k direction when you put 0 in for t. Did I do that right? Because I have 0t, 0, t is equal to 0, so this whole thing is 0, and I have minus 1/4 e to the 0, which is 1. Okay? Now this is a part that you don't want to forget. There's a plus c in there. And then you're supposed to set this equal to each other because they're supposed to be equal. And so when you set that equal to each other, there's a constant here that you're going to be looking for. So c is equal to, I guess I should write this out first. So 1j minus 1/4 k plus c is equal to ijk. And so c is equal to, I doesn't change, the j and the j cancel, so that's nothing. And then you have 1 plus 4k, 5/4. Right, 1 plus 1/4, that's 5/4. So that's c, and if I just tack that onto here, then I would get my result. So my answer then should become R of t is equal to, now that I have this all together, I want to group my i's together. So I got 1/6 t to the 6 plus 1. The plus 1 comes from here in the I direction. My j direction is just e to the t, and there's no j over here, so there's nothing to add. Pardon me? Because this is 0. What? Where? That's because, so I'm solving for c here. Yeah. And then this ijk came from here. Yeah. And so if I solve for c, I would subtract the j over. subtract this k over. So let's take a look at it and make sure it's correct.
No, I see.
But everybody else, can you guys just make sure that I'm doing things correctly here? Yeah? All right. Because I don't want to make a mistake early on and then at the end of the problem and figure out that we made a mistake early. Okay, so that's my J. My K looks like this long string and then plus the constant 5/4. So I'm going to put that all together. That should be blue. T e to the 4t minus 1/4 e to the 4t plus the constant 5/4 in the k direction. So that should be my result. Okay, questions? So this technically is an example of a differential equation. If you've taken differential equations before, you'll see that this is an example of an initial value problem in differential equations. Okay. Any questions? Anything else talked about here, or we move on? Okay, there's some people that don't want to look. They just I guess yeah, let's just move on. All right. So we're going to move on to the next section, which is finding arc lengths. And so we're able to look at motion. We're able to find derivatives and integrals of things. We're going to, in the last section, I don't know why they put it in the last section of this chapter, but in the last section they're going to talk more about the motion, the projectile motion type of problems that you guys might have seen in Calc 2. But that's a good application for the integral. But before that, they talk about arc lengths and curvatures and things like that. So we're going to study the geometry of the line. And so let's get this in our notes. Yeah? Arc length and curvature, yeah. I didn't have a title. Did I have a title? No, I don't have a title. Yes, arc length and curvature. All right. So the idea is for us to find arc lengths and then find the curvature. We'll define the curvature and find it and then identify a tangent line. Or tangent circle this time. So we'll talk about what a tangent circle means, and it's intimately tied into the whole idea of the curvature, which is kind of neat. And arc lengths. So let's I think I kind of sketched out a sketch. I think we saw something like this before. Remember the arc length for a parametric curve? For x of t, y of t. And then I think we called it S or something, is equal to the integral, and I don't know if they use alpha and beta or A and B. They use A and B. And then it was something with the square root of the derivatives squared added together or something like that. Remember that? So it turns out if you're going to go three-dimensional, it kind of, the Pythagorean theorem kind of happens in 3D also. The x squared, x prime squared, y prime squared, and z prime squared. So you'll have three components here instead of just two. And what we're going to do is we're going to write that a little bit neater, and we'll see that in a minute. So in 3D, remember these vector valued functions are essentially parametric equations just put into a nice vector form. So we can also identify them as three-dimensional parametric equations. So our length is going to be parametrized by t, so you'll have some t values, a t value starting point and a t value ending point. We'll just call that a and b. And then this time we'll extend this square root to tack on another component. So we have the x prime of t squared plus y prime of t squared plus z prime of t. So this is going to be our working definition. If you look at the formula that I had and that they had in the book, you'll see that it looks like it's a little bit simpler. I don't know if it looks simpler. Let's take a look. Oh, they make it a little bit more compact into this little thing, r prime with a magnitude. What's r prime with a magnitude? Well, it's the same thing. It's equal to that. It's the derivative. It's r prime is the derivative. Taking the magnitude, you square the components, you add them, you put them under a square root. So that's exactly what it is. So it turns out that here's a nice, more compact formula for your arc length. I mean, if we're going to actually do the computation for the arc length, it's still going to require us to find the derivatives and square them and add them and put them under a square root and everything else. So it's still going to be a considerable amount of work. So here's your shortcut, at least shortcut in terms of the formula. So let's do a quick example, and the nicest example in 3 dimensions would be helices. So let's take a look at an example where we're finding the arc length of a helix. Yeah. So we'll see. Let r of t equal to cosine of t, sine of t, and let's just say t. So this is like a circle. If you imagine your wire circle and then you stretch it up into a spring, then this is what this is. And let's be clear about our limits here. Let's let t go from 0 to 2 pi. So we know that the circumference of a circle is 2 pi, right? And so this is a circle that's been stretched out, and so I think maybe that the circumference might change a little bit. So let's see how that's going to change, or maybe it'll be the same. Anyways, let's do the thing, the formula. So the arc length is going to be an integral from 0 to 2 pi. The square root of the derivative of the cosine is sine, negative, but I'm going to square it anyway, so I'll just put sine squared t. The derivative of sine is a cosine. I'll square that. That'll be cosine squared t. And then the derivative of t is 1. Yes, sine squared, cosine squared, and so this is why I kind of chose the helix, because otherwise you get some complicated functions, you're going to get some weird looking things, and a lot of times these things are not, I mean, you can really work hard to integrate them, but you would give them to a Calc 2 student and say, here, integrate this for me. I meant put it into Wolfram alpha. So this is square root of 1 plus 1. Yeah, this is just square root of 2, which is a constant. 0 to 2 pi, square root of 2 dt. So this is just square root of 2 times 2 pi minus 0. So here you go. Now, I don't know if we talked much about this, but if you have a curve, like a circle, or in this case a helix, it turns out there's an infinite number of ways to parameterize that curve. What does that mean? So that means if I had another curve, R2 of t. Oh, this would have been a good time for an R2D2 joke, but I don't have one. Cosine of 2t, sine of 2t, and then 2t, I guess. And then let my t limits go from 0 to pi. Well, this is going to draw the exact same thing. I hope. Should it? So you could check the endpoints. You could check where it starts and where it stops. You can check maybe a middle point. Like when t is equal to pi on this parameterization R, you can check to see what happens when t is equal to pi over 2 in this parameterization R2. And then we'll see that we're going to get the same result. So same curve. Same arc length. All right, there's a point to this that I'll have to wait till next time to make a point of since it's late. So we're going to parameterize a certain way to make some certain theorems look nicer and work nicer for us. We'll talk about parameterizing by arc length next time. Okay, see you guys